So in our third video here in Module 13, we're going to talk about solving equations with logarithms, solving logarithmic equations. And we have two properties that we can use. The first thing is this property of logarithmic equality, and we were just using it in the last section. And basically what it says is if we have 1 log equal to 1 log and the bases are both the same, then the arguments must be equal. So we could say that m equals n. But again, it has to be 1 log equal to 1 log. If you have 2 logs on one side of the equation, you're not going to be able to use that property correctly. So we'll use our properties of logarithms, our power, quotient, and product rules to condense logarithms on one or both sides of the equation so that we can use this property. And then the other situation occurs when you have a log, 1 log equal to a number or some value. So if you have 1 log equal to a number, you convert. If you have 1 log equal to 1 log, you're going to drop the logs. And you do need to remember that we can have extraneous solutions because the argument of a logarithm must be greater than 0. So you're always going to want to check and make sure your solutions work. All right, so in these first examples, 14 and 15, we're going to be able to write them as 1 log equal to 1 log. So what that means for us, on the left side of my equation, in example 14, because I have that minus in between the 2 logarithms, I can condense them and write them as 1 log. So what this would look like would be the natural log of, the numerator would be the first argument, 12, over the denominator, the second argument, x plus 1. And that would be equal to ln 4. So now that I have 1 log equal to 1 log, I can allow those logarithms to be equal to each other and drop my logs. And so then I'm faced with solving a rational equation. I've got 12 over x plus 1 equals 4. Keep in mind that 4 is over a little invisible 1, so we can cross multiply, and I'll get 12 equals 4 times x plus 1. 12 equals 4x plus 4. Subtract the 4, you get 8 equals 4x. And dividing on both sides by 4 will give you that x equals 2. So you just want to make sure that that answer checks. And if I take it and plug it in right there, at the top, I would be getting the natural log of 12 minus the natural log of 2 plus 1 is 3 equals the natural log of 4. And 12 over 3 equals 4, so this will check. So let's solve example 15. Again, we want this to be 1 log equal to 1 log. And we have 2 log 7x equals log 7 64. So the way it stands right now, it is not 1 log on the left, it's 2. But if I use my power rule, that's going to give me log base 7 of x squared equals log base 7 of 64. And at this point, since I have 1 log base 7 on the left and 1 log base 7 on the right, I can drop the logs and let those arguments be equal to each other. So here I get that x squared is 64, and if I square root both sides, that's going to give me that x equals plus or minus 8. The square root of 64 is either positive 8 or negative 8 in this situation because we're solving. So we have to ask ourselves, would both of those answers work? X equals positive 8 and negative 8. And if I go and try to plug negative 8 back into my equation, one thing we know is we can't take the log of a negative number. So in this case, we end up with a extraneous portion of our solution. Okay? So the goal here, if you have a log on either side of the equation and there's no constant, would be to write them as 1 log equal to 1 log. So we have examples 16, 17, 18, and 19 left. And what we want to notice about these examples is that they all have a constant term. Okay, so they all have a value that's just a number. So in these situations where we have a constant, this is going to be like a log equal to a number, like this rule. And we're going to convert into an exponential equation to solve. So let's get rid of those circles I drew. So example 16, if we convert this, this would be the same as writing 5 to the negative 3 equals x. And 5 to the negative 3 is 1 over 5 cubed, which is 1 over 125. So x is equal to 1 over 125, which in this case, that value will check. Okay, so example 17, this 1/2 is going to go right in here on the x. If we're converting, and that would become x to the 1/2 equals 9, or squaring both sides, we would get x equals 9 squared, x equals 81. On to example 18, 6 times log base 2 of 4x minus 7 equals 18. And there's more than one way to go around these problems. We just have to make sure that we're using all of our rules properly. So one thing which we've been doing a lot would be using the power rule of logs, and that would allow me to put 6 up on the exponent of that argument. But in this situation, I'm going to choose, since that's 6 times a log, to divide by 6 on both sides of the equation. And that gives me that log base 2 of 4x minus 7, 18 divided by 6 is 3. So now, if I convert, the conversion, this is going to be 2 cubed equals 4x minus 7. 2 cubed is 8. 8 equals 4x minus 7. I'll add 7 to both sides. That gives me 15 equals 4x. And then dividing by 4, I'll get x equals 15 over 4. And of course, this will also check. If I plug that into my argument, it's going to remain positive. And that's the main thing we're looking for when we're solving this. Okay. So on this next one, we have 2 constants. So we start getting into a little bit more rearranging of the equations. I can collect those constants to one side. And in this situation, when I'm dealing with 5 plus ln x plus 2 equals ln 3 plus 6, I'm going to subtract 5 from both sides of the equation, which gives me the natural log of x plus 2 equals the natural log of 3 plus 1. So we have a few options here, but the main thing is we want to get that constant alone. So I'm going to subtract ln 3 to the left side of the equation, which gives me the natural log of x plus 2 minus the natural log of 3 equals 1. And putting parentheses around the 3 is cosmetic. whatever helps you understand it, but you don't need those there. You do need them around the x plus 2. That's important because we want to make sure both of those remain in the argument. But the 3, that's really a choice. So now that I have 2 logs and we have a minus between them, I'm going to rewrite that as ln of x plus 2 over 3 equals 1. So I have 1 log equal to a number. And working on this problem here, natural log, we have to say, well, what's the base? And we know there's a little invisible base e here. So if I convert this to an exponential equation, I'm going to get e to the first equals x plus 2 over 3. So I've converted e to the first equals x plus 2 over 3. And I don't really need to write that 1 there. So now, again, we're just trying to isolate x. We're solving for x. So I'm going to multiply by 3 and then subtract 2. So I end up with x equals 3e minus 2. And that is my exact answer. Of course, I can type this in my calculator as I want, and I'll get that it's approximately 6.15. And then at the end, we always remember to check, and in this case, 6.15 does check in the original problem. Okay, we have 3 examples left in this module. So example 20, log base 6 of x plus 4 minus 1 equals negative log base 6 of x plus 3. So because we have one term that's a constant, we always want to try and isolate that on one side, and then we're going to get the logs on the other side and then condense them together. So in this situation, I'm making a choice. I'm going to move this log to that side and the constant over there. So that gives me log base 6 of x plus 4 plus log base 6 of x plus 3 equals positive 1. So I have 2 logs on the left equal to a number on the right. And because I have a plus sign between those 2 logs, I'm going to use my product rule. My product rule means I'm going to multiply those 2 arguments. And multiplying those 2 arguments gives me x squared plus 7x plus 12, which is equal to 1. So now that I have 1 log equal to a number, we convert. And when I convert this, this becomes 6 to the 1 equals x squared plus 7x plus 12. So we're done with logarithms. And so far, when we've been solving and we've gotten rid of our logarithms, everything has been linear. But in this situation, we have a quadratic equation. And so when we're dealing with quadratic equations, we always want to make sure that we write them in descending order equal to 0. So 6 to the first is just 6. I'm going to subtract 6 from both sides, and I get 0 equals x squared plus 7x. Subtracting that 6 from 12 gives me positive 6. And this is going to factor. In this case, I'm going to get 0 equals x plus 6, x plus 1. They're not, in the real world, they don't always factor. But for the purpose of this class and what you'll see, most likely when you get something quadratic, it should turn into something factorable. So in this situation, we end up with x equals negative 6 and negative 1. But we still need to check. So just because they're negative doesn't mean I have to throw them out. We know we have to take the log of a positive value, something greater than 0, but it doesn't mean it can't be negative. So we want to look at what happens when I plug -6 or -1 in. So if I were plugging -6 into, say, log base 6, -6 plus 4, that would be log base 6 of -2. And I can't take the log of a negative number. So -6 is extraneous in this situation. Only x equals -1 works. All right, example 21. Negative log base 2 of x plus 1 equals 3 minus log base 2 of x minus 6. So again, I have a constant. I'm going to rearrange and isolate that constant. So adding the log to both sides, I'm going to end up with log base 2 of x minus 6 minus log base 2 of x plus 1 equals 3. So the way I rearranged it, I just moved my terms around so that I would have a positive in front, because this was negative on the right. When I moved it to the left, it became positive. So this simplifies to log base 2. My argument, because we have a minus between these two logs, becomes x minus 6 over x plus 1 equals 3. So 1 log equal to a number, we convert, and that's going to become 2 cubed equals the argument. So 2 cubed equals x minus 6 over x plus 1. And so 2 cubed, in an effort to save some space, 2 cubed becomes 8. Now I'm dealing with solving a rational equation. So if I think about that 8 as being over an invisible 1, I can cross multiply, which gives me 8 times x plus 1 equals 1 times x minus 6. Or 8x plus 8 equals x minus 6. So now we're solving a linear equation. I'll subtract x from both sides. I end up with 7x plus 8 equals -6. I will subtract 8 from both sides, and now I have 7x equals -14, and dividing by 7 I get x equals -2. Now, when I go to check, what happens when I try to plug -2 in here or here? If I plug -2 into x plus 1, I get -1. And if I plug -2 into x minus 6, I get -8. So in both of those situations, we get a negative number for the argument, which is not allowed to happen. So our answer here is no solution. And we have one final example. Example 22, log of x equals 2 minus the log of x plus 15. So again, log equal to a number. I'm going to rearrange by adding the log on the right to the left side of the equation, which gives me the log of x plus the log of x plus 15 is equal to 2. Because those two logs have a plus in between them, I'm going to multiply my arguments, which gives me the log of Multiplying that is x squared plus 15x equals 2. So we have 1 log equal to a number, and we need to convert that. Oh no, where's the base? Well, what we want to remember is that when there is no base written and it says log, that means it's a common log and there's a little invisible 10. So converting this is going to become 10 squared equals x squared plus 15x. 10 squared is 100. So I have 100 equals x squared plus 15x. And now, because I have an x squared, I know it's quadratic. In quadratic equations, we put in descending order equal to 0, and we factor. So we're looking for 2 factors of negative 100 that are going to sum to equal positive 15. I've got 0 equals x plus 20 and x minus 5. So my solutions are x is negative 20 and positive 5. And then again, we have to check, do both of them work? And if I go back to that very first log, I can't plug a negative in there. So negative 20 is extraneous, and the only solution we get here is x equals positive 5.